Screen visible है?
Yes, sir.
Okay, जी. So let's start the next topic, which is about nozzle efficiency. So far, whatever we have discussed about nozzle, we have used one major assumption that the flow through that nozzle is isentropic. So isentropic simply means there is no frictional effects. So, for example, this is our nozzle, and fluid is flowing through that nozzle isentropically. So it means we have neglected friction between the fluid and the walls of that nozzle. So, but actually we know whenever there is a fluid flowing through any pipe or through any duct, there will be friction between the fluid and the walls of that passage or pipe, right? And therefore there will be a friction and that will produce heat, and this heat will make this process non-isentropic or non-adiabatic. So that's why we can account for this non-isentropic effects or the effects of this irreversibility by using that term which is known as nozzle efficiency, right? So this nozzle efficiency or is actually telling us that the fluid flow is through this nozzle is not purely isentropic. And the difference between this isentropic and non-isentropic fluid flow is actually defined as nozzle efficiency. So, so here, for example, you see if the fluid is flowing through a nozzle, and that is a steam nozzle. For example, this point one represents the inlet of that nozzle, point one, and that is, for example, point two, exit of nozzle. At point one, if it is steam nozzle, then steam is entering into that nozzle as superheated steam. So here you see this point one represents the superheated point. Point two represents the exit of nozzle. Now, if we assume it is an isentropic process, then on this TS diagram, on this T versus S diagram, point two will be exactly vertical from this point one to point two. If we assume isentropic, which means S1 is equal to S2. And here, specifically for isentropic, we are using this subscript S. So for isentropic flow, I will say it is 1 to 2s. The process is 1 to 2s, but in for non-isentropic flow, there will be some entropy generation, right? So at this point, some entropy will be generated, and this is the actual point 2, right? Because entropy during this process is increased. S2 is greater than S1. So S2, entropy at point 2 will be actually greater than entropy at point 1, right? So can you all hear me? Just मुझे दोबारा confirm कर.
Yes,
Yes,
sir.
sir.
Alright. अगर दरम्यान में कहीं डिस्ट्रप्शन हो या कनेक्शन लॉस्ट हो जाए तो आप मुझे व्हाट्सएप के थ्रू इन्फॉर्म जरूर कर दीजिएगा, एनी वन ऑफ यू, ठीक है? सी आ गया. ओके, सो here you see point 2, why point 2 is here in the superheated region, because due to the non-isentropic effect, some friction is there, and due to this friction, some heat is generated, and where this heat will go, this heat will go to the fluid itself. That's why you see here it is the temperature at point 2 is actually a greater than temperature at point 2s. This is the case for steam nozzle, because in case of steam nozzle, the point 1 is entering as superheated steam, and point 2 may be within the dome. Some fluid or some part of the steam may have been converted into liquid. Because inside the nozzle, we know when pressure drops, temperature also drops. So when temperature drops and pressure drops, the boiling point also drops. So that's why this point could be inside this dome. This is just an example. Actually, there could be a situation where this point one is here. You are starting from here, and point 2s would also be here in the superheated region, and then point 2 will be somewhere here. So it's not necessary that always point 2s will be inside the dome. So it depends from where the point 1 starts. And what is point 1? It is, in case of steam nozzle, this is the steam coming from boiler. So, but the main thing is that we should know what is the difference between 2s and 2. So here we will be using from this point onwards, or from this topic onwards, we will be using S subscript for isentropic and without subscript for actual or non-isentropic process. All right. So similarly, so this figure is for vapor, and we have already discussed that vapor means non-ideal gas, or in our case, it will be steam. Right. So actual process is 1 to 2, and isentropic process is 1 to 2s. Similarly, so that is shown here. Now for a perfect gas or for an ideal gas, the same figure will be shown like this, because now we are in the superheated region, definitely, or in the gaseous region. And for gases, there is no need to show this dome, because normally these points are far away from that dome. So here you see P1 and P2 pressure lines in the gaseous region, somewhere here. Right. So that's why there is no need to show the dome. So here again, point 1 to 2s represents the isentropic expansion, and 1 to 2 represents the actual or irreversible adiabatic expansion. Right? Because now there are losses due to friction. So now based on these two processes, one is isentropic, other is a non-isentropic, we can define the term efficiency. Right? So normally this non-isentropic effects are only 10 to 15% normally in these nozzles. So based on this, we can define the nozzle efficiency. Here the same processes are shown on HS diagram for steam. Here you see the dome on HS diagram, and TS diagram for perfect gas. So again, the same 2 points, 1 to 2s and 1. So here, how we define nozzle efficiency, it is the ratio of actual enthalpy drop. Actual enthalpy drop is H1 minus H2, H1 minus H2, divided by the isentropic enthalpy drop. Here you can see isentropic enthalpy drop is more, 1 to 2s. The magnitude or the difference between 1 and 2s is more than the difference between 1 and 2. So here on y-axis, you can see this is H1 and this is H2s, and this is H2. So you can see the difference between H2 and H2s on y-axis if it is HS diagram. So based on this, we can define nozzle efficiency as actual enthalpy drop, which is H1 minus H2, divided by isentropic enthalpy drop, which is H1 minus H2s. So that's how we define nozzle efficiency. And we also know how to calculate all these enthalpies using steam table or HS chart if it is a non-ideal gas like steam. And for a perfect gas or for an ideal gas, we can write this equation as by replacing delta H with Cp dt. So it is Cp into T1 minus T2 and divided by Cp into T1 minus T2s. So we can write this nozzle efficiency in terms of temperature also. If we assume this Cp as constant from 1 to 2 or from 1 to 2s, if Cp is constant, then Cp will cancel. So here we have nozzle efficiency in terms of temperatures also. Even actual temperature drop divided by isentropic temperature drop. And here you can see isentropic temperature drop is more 1 to 2s than actual temperature drop, which is 1 to 2. Similarly, now we can also define this nozzle efficiency in terms of velocities also, because as we already know, for the exit velocity, we have represented by C2 for actual velocity and C2s for isentropic velocity. So just like temperature and enthalpy, now we can also show velocities as actual velocity at exit divided by isentropic velocity at exit. And we already know this steady flow energy equation, or first law of thermodynamics for a nozzle, gives us this equation: enthalpy at inlet plus kinetic energy at inlet is equal to enthalpy at exit and kinetic energy at exit. This is for the case of isentropic, because here you see 2s. So from here we can write h1 minus h2s in terms of velocities, which we already know. Similarly, we can define another efficiency, another equation of energies, h1 plus c1 square by 2 for non-isentropic process. For process 1 to 2, here is another equation. So similarly, we can write delta H, actual enthalpy drop, in terms of kinetic energy change. This is kinetic energy isentropic. This is actual kinetic energy change. So now we can write the same nozzle efficiency in terms of these kinetic energies. We can replace H1 minus H2 with this term and H1 minus H2s with this term. So that is what we have done here. So now we have nozzle efficiency in terms of kinetic energies: C2 square minus C1 square over C2s square minus C1 square. So if C1 is normally, we assume it is negligibly small compared to C2 or C2s. So if we neglect C1, so the nozzle efficiency is simply given by C2 square over C2s square, right? So now we have seen three different forms of nozzle efficiency: one in terms of enthalpy, second in terms of temperature, and here is the third one in terms of kinetic energy or velocity, right? So now we can see that the nozzle efficiency, why we are defining this term nozzle efficiency, because there is friction. Whenever there is a fluid flow through a pipe, it experiences friction, and due to friction, we have to define this efficiency, which is not 100%, because we cannot avoid friction or the heat generation due to frictional effects. So maybe you have already studied in fluid mechanics, flow through pipes already पढ़ लिया है, या maybe you are studying nowadays. फ्लो थ्रू पाइप्स आप लोगों ने पढ़ा है?
Yes, sir. पढ़ रहे हैं, sir.
पढ़ लिया.
सर आज पढ़ रहे हैं सर.
Okay. There you also would have learned about Darcy's equation, about head loss for a fluid flowing through a pipe.
Yes, sir.
That equation is FL V square over 2GD. Darcy's equation. So here you can see this Darcy equation is actually telling us the amount of energy loss to overcome friction. And here you can see the because it's next. So from here we can understand the effects of friction on a fluid flowing through any duct. It could be a constant area duct, right, simple pipe, or it could be a nozzle like this one. So here you can see this friction, or in other words, the nozzle efficiency depends upon the material of the nozzle, because where is the effect of the material in this equation? Is Darcy's equation, type of material का effect कौन सी term है?
F.
F, right? Then size and shape of the nozzle. Size means how long this nozzle is. So here is the effect. Length. Greater is the length, greater will be the losses. And shape. What about the shape of the nozzle? It could be a circular cross section nozzle, it could be rectangular, square, or any other shape. So that effect of shape will also be here somewhere in this equation. One is this one, D. This D represents the effect of shape. If it is circular, then it will be D. If it is non-circular, then what we do, अगर आपने study किया, for non-circular pipes, we replace this D with hydraulic diameter. Right? यहाँ पे भी उसका इफेक्ट आता है और F में भी आता है. F में you have Reynolds number. Right? So Reynolds number maybe you have to define rho VD over mu. So there again this D appears. So D is diameter for circular ducts, or if it is circular cross-sectional nozzle. If it is non-circular nozzle or non-circular pipe, then we have to replace it with hydraulic diameter for A over B. So all these factors are actually affecting the efficiency because all these factors are contributing to frictional effects. Right. So that's why we can say that the nozzle efficiency is dependent on the type of material, means F, size, L, shape, T, and there are other factors like this angle of divergence, because now it's not a constant cross-sectional area. So that will also affect somehow this D, because D is not constant. So then also the nature of fluid which is flowing, whether fluid flowing through this nozzle is air or steam, that will also affect, because how this affect the nature of fluid effect appears here. Where is the nature of the fluid or type of the fluid in this equation?
Velocity.
Velocity is
Renault
Reynolds number. Velocity तो कोई भी fluid हो उसकी same ही velocity होगी. So it is again Reynolds number, which is this factor F. Right. So it means nozzle efficiency depends upon nozzle material, its size, its shape, and also this angles of divergence and convergence. अभी इसको हम further detail में study करेंगे. Right. So that's why whenever we want to design this nozzle, so all these parameters has to be taken care of for creating a very smooth nozzle, so that the effect of these friction are as minimum as possible. And we want to approach this ideal process, which is the isentropic, means friction-free process. Okay. So then there is another term which is known as velocity coefficient. That is the ratio of actual velocity at the exit to the isentropic velocity. Because here, this is not velocity, this is actually kinetic energy. So in terms of velocity, if we represent the same ratio as C2 over C2S, then it is not efficiency, then we name it as velocity coefficient. So velocity coefficient is given as C actual at exit divided by C isentropic at exit. So it is not C square, so it is the velocity coefficient. So this is another term which can be used to describe the performance of nozzle, and that is called velocity coefficient. Right. So this is represented as C2 over C2S. Then there is one more term which is known as coefficient of discharge. Actual discharge, here discharge means mass flow rate. Actual mass, which is leaving the nozzle, divided by maximum mass which can flow through that nozzle when the flow is isentropic. So here we can define one more term to describe or designate the performance of a nozzle as m dot over m dot s. So again, here S simply means for isentropic. So actual mass flow rate divided by isentropic mass flow rate is known as coefficient of discharge. All right. So now we have all these equations are related to nozzle performance in terms of efficiency or in terms of coefficient of velocity or coefficient of discharge. So now the numericals which you will solve there, you will be solving an actual nozzle by disregarding the ideal concepts. तो अभी तक हमने जितने भी numericals किए थे, we were assuming that flow through a nozzle is isentropic, free of any losses. But if losses are there, then we can use all these various definitions to account for those losses. Okay. So now, next, we shall now discuss about the length of nozzles, because so far we haven't said anything about the length of nozzle, how this length of nozzles is normally chosen for the convergent section and also for the divergent section. Now, of course, we know within this nozzle, as the velocity is increasing, the frictional losses are also increasing, as we have seen here, because the frictional losses, HF, the head loss or the pressure drop due to velocity is quite significant because it is directly proportional to the square of velocity. So that's why inside the nozzle, we know velocity is increasing. So with the increase in velocity, the losses in terms of head loss or pressure drop also increases, right? And so that's why here we see when we are using a convergent divergent nozzle, it simply means the purpose of that nozzle is to attain supersonic velocities. It means in this portion that this divergent portion will experience maximum velocity, and that's why the maximum frictional losses, because velocities are already in the supersonic region in this entire divergent section. So that's why frictional losses are found to be more in this section after throttle, right? In this convergent divergent nozzle, right? So because the velocities in this section, in this convergent section, are much smaller than the velocities in this divergent section. So significantly high friction loss in this divergent portion of the nozzle are experienced compared to the convergent section of the nozzle. So now the question is how the length of that nozzle is normally decided. The length of this convergent section, this one, is normally taken very small. Up from inlet till throat, the length of convergent section up to the throat is normally very small compared to the length of this divergent section. Now we shall discuss why the length of convergent section we take it very small and why the length of this divergent section is taken long. So first I will explain the convergent part. The length of this convergent portion should be as small as possible, this length from this point till this point, to reduce the surface friction, right? And normally this length could be as small as only 6 mm. This length nozzle in the convergent section could be as small as 6 millimeter only. Because we have already discussed how to calculate the throat area and how to calculate the exit area to attain certain C2, and for a certain M2 we can calculate A2 and AC. So now you can define, once AC is known, then from inlet till exit, from inlet till throat, we can make it as short as possible, like this one. Or you can make it like this one, a little longer, to reach the same areas. Areas defined by this cross section, right? Same cross section, but here we are using very small length, and here we are using a bit longer length to reach the same throat area from inlet to this throat, right? So we should choose a very small length, as small as possible.
एक्सक्यूज मी सर।
जी।
सर फ्लूइड के अंदर हमने पढ़ा है कि ना जो बाउंड्री की वॉल्स होती है ना, वहां पर जो वेलोसिटी वो बिल्कुल जीरो होती है, और ऊपर जाते जाते ना वो वेलोसिटी कुछ इंक्रीज होना शुरू हो जाती है।
हम्म।
फिर
हम्म।
मिड के अंदर एक लाइन आती है जहाँ पे ना वेलोसिटी मैक्सिमम हो जाती है। कि
हम्म।
लेकिन ऊपर वाली सरफेस और नीचे वाली सरफेस वो मिलती हैं जाके, उनको ना काफी मैं कि थोड़ा एरिया चाहिए होता है, फिर जाके वो एक पैराबोलिक शेप बनाती हैं वेलोसिटी, और वो
हम्म।
कॉन्टिन्यूस हो जाती है। तो सर अगर
हाँ।
6 mm रखेंगे तो ये तो बिल्कुल बहुत स्मॉल होगा, इस तरह तो उसकी शेप वो बन ही नहीं सकेगी प्रॉपर।
हाँ, आप जो बात कर रहे हैं ना, वो इस कांस्टेंट क्रॉस सेक्शनल एरिया पाइप की बात कर रहे हैं।
एग्जैक्टली सर।
हम इधर बात कर रहे हैं कन्वर्जेंट सेक्शन की। यहाँ तो दिस शेप इज एक्चुअली मेकिंग दिस फ्लूइड टू मूव इन अ पर्टिकुलर डायरेक्शन। ठीक है। यहाँ वो उस तरह से बाउंड्री लेयर नहीं डेवलप होगी। ठीक है, बिकॉज इट इज कन्वर्जिंग सेक्शन, सो ऑल द फ्लूइड पार्टिकल्स विल बी मूविंग इन towards this smaller area, from this larger area to this smaller area. अब आप वो जो बात करें देखें, अदरवाइज अगर आपने वो बाउंड्री लेयर डेवलप करनी, देन इट शुड बी एज लॉन्ग एज पॉसिबल। ठीक है, कि वो बाउंड्री लेयर पूरी तरह डेवलप हो जाए। बट उसका नुकसान क्या होगा? यू आर इंक्रीजिंग द लेंथ। ठीक है, वी आर टॉकिंग अबाउट विद रिस्पेक्ट टू फ्रिक्शन। वो जो आपने टॉपिक पढ़ा है ना, वो है इन कि कोई लॉन्गर लेंथ का पाइप है, तो देन व्हाट इज हैपनिंग, देन दिस इज that's how the boundary layer is developing. Here, there is no need to reach that level because you are increasing the length. As the length is increasing, frictional top is increasing.
ओके
So
सर,
this
थैंक
situation is different, entirely different from this situation because it is not
ओके सर।
constant area. अगर constant area भी हो तब भी आपने length को तो length के effect को तो neglect नहीं करना. So as the length is increasing, the frictional losses are increasing. So that's why the length of this convergent portion should be short in order to reduce the surface friction. Right. So this length could be as small as 6 mm. Right. So this rapid change in this area is possible because the convergence of these walls of this passage will tend to stabilize the flow. जैसे मैंने यहाँ show किया. So but in the divergent section, the situation is different. So first of all, I have explained the convergent section. Convergent section may it should be as small as possible, right? Because we already know what is the throat area. So throat area, you can reach this throat area in a very small length. You can reach the same throat area in a longer length. So there is no need to have a longer length in case of convergent nozzle or the convergent part of the convergent divergent nozzle. Now let's discuss about the divergent part. Divergent part में issue ये है कि the fluid velocity here in the divergent part is already very high. So in the divergent portion, this high velocity stream which is leaving from here, for example, this is the convergent part, and divergent part is, for example, very short, like this one. This represents AC, and this represents A2 at exit. So let's first consider the case where this divergent part is very short in length. Then what will happen? So in this divergent part, we already know the fluid velocity will be very high. So in the divergent part, this high velocity stream has a tendency, um, because of this inertia, that it will not occupy this whole space. This fluid will try to follow the same diameter of this throat. Because of very high velocity, fluid will try to follow the same path, this one. Right? It will not occupy the whole area of this divergence. Actually, it should occupy this whole area because area should increase to increase the velocity. Right? So that's why this flow in the divergent part will be of in the form of a circular jet, like यहाँ पे show किया, in the form of circle, because this fluid is not occupying this whole area of this divergent part, because the divergence angle is very large. अगर मैं यहाँ पे define करूँ what is divergence angle and define this angle as divergence angle. Let me name it as theta. This theta is too large because we have made this divergent portion very smaller. Right. So that's why when the fluid is leaving this convergent part, it will not occupy the whole portion of this divergent part. It will try to flow in this circular jet form, like here shown. Right. So that's why steam will not occupy this increased area. This increased area. So steam may pass out through this divergent point without any drop in pressure. This fluid is not flowing through this entire area. Right? So that's why, to avoid this phenomena, the divergent portion should be kept sufficiently long, right? So that this steam has enough time to occupy this whole space with smaller divergence angle. मैं इसको दोबारा से explain करता हूँ. Now you know A2. Now to achieve this A2, this is for example convergent area. Now you can achieve the same A2 in a very small length, or you can achieve this same A2 in a larger length or a longer length. This one. Now here, this A2 is similar to this A2. This A2 and this A2 in both cases is similar, but here the divergent portion is long, here the divergent portion is very small. So when this divergent portion is very small, then the fluid may not be occupying this whole cross section, this whole passage. And the fluid velocity will not be increasing, because in the divergent portion, we want the fluid area to be increased. Right? Here, the fluid area will definitely increase. So, but here, issue here, the length will be increasing. So here, the frictional losses will be more compared to this case. But here, the fluid will occupy this whole area. Right? And that's why the fluid velocity will definitely keep on increasing here, although you will be losing some energy to overcome friction because of longer length, but that is now a compulsion compared to this case. यहाँ पे फिर आपको velocity ही increase because fluid is not occupying the whole area, and here we want the fluid passage area to be increased to reach higher supersonic velocities. And also there is one more phenomena which is known as flow separation. Here, when the fluid will leave this convergent section, it will be already at a very high velocity. Okay. And now there will be a fluid separation within this space because the fluid cannot occupy this whole space. So ये जो fluid separation की वजह से भी there will be some reverse flow like this one. Because this passage is very, fluid is coming out, and there is some flow separation like this one, because it cannot occupy this whole space. So that is the reason why this divergent portion is kept longer. How long? उसके लिए कुछ empirical correlations हैं जो मैं explain करता हूँ. So that was the major reason, that is that we have a gradual increase in area in case of divergent portion, right? So how long it should be, उसके लिए भी कुछ rules of thumbs हैं. This angle, ये जो angle मैंने यहाँ पे show किया, the divergence angle, it should be around 10 to 25 degree, not more than this. If this divergence angle is more than 10 to 25 degree, then we will have this phenomena of flow separation, and the fluid will not be occupying the whole cross section area, right? So that's why the divergent portion is kept longer. Convergent portion should be as small as possible, because here there is no issue of such flow separation, right? Because here the whole fluid will be converging, so all the fluid particles will be moving in one particular direction. So here, to keep the friction minimum, the length should be as minimum as possible, right? So yes, slides क्यों मैं explain किया हुआ in detail, so I've explained it here. मैंने यहाँ show नहीं कर रहा जी
सर ये डाइवर्जेंट पोर्शन का जब लेंथ लंबी
जी
लॉन्ग करेंगे तो सर इसकी फ्रिक्शन लॉसेस ज्यादा होंगी तो वेलोसिटी भी सर इफेक्ट पड़ेगा ना सर।
हाँ, वो इफेक्ट जो है वो नेग्लिजिबल है कंपेयर टू इस इफेक्ट के। यहाँ पे फ्लूइड पूरे ये जो स्मॉल डाइवर्जेंट पोर्शन में फ्लूइड इज नॉट ऑक्यूपाइंग द होल स्पेस, यहाँ तो वेलोसिटी इंक्रीज ही नहीं होगी, वहाँ एटलीस्ट इंक्रीज जरूर होगी, कुछ पार्ट फ्रिक्शन में लॉस होगा, ठीक है। इफ यू मेक अ गुड स्मूथ नोजल देन दैट फ्रिक्शनल इफेक्ट विल बी कैन बी केप्ट एज मिनिमम एज पॉसिबल, बट इस केस में विद लार्जर डाइवर्जेंस एंगल velocity will not increase because fluid will be flowing like this one, like a pipe, यहाँ से convergent section से out होने के बाद। If this divergence angle is too high, ठीक है, वो एक constant वही sonic velocity के around ही move कर रहा होगा because it is not occupying the whole cross sectional area. So area has to be increased, ठीक है, तो वो एक sudden increase नहीं किया जा सकता, so you want to have this gradual increase. So velocity कुछ drop होगी, लेकिन at least you will be in supersonic region. Here, supersonic achieve nahi hoga. So that's why here we have to compromise two parameters. One is the velocity drop due to length, increased length, but that will be smaller compared to very large divergence angle. So angle of divergence in this divergent portion is normally kept between 10 to 25 degrees to avoid this flow separation phenomenon. Okay, so therefore a compromise should be adopted in selecting this divergence angle. So we now have studied that a very small angle is desirable from the flow separation point of view. You want to keep this divergence angle as small as possible so that there is no flow separation. But this is undesirable due to a very long length, because then long length means larger frictional losses. So you have to compromise between these two phenomena. So that's why the length of divergent portion can also be calculated using this empirical formula based on the experimental data. This length of this divergent portion can be taken as 15 into area of throat under root. So this will ensure that divergence angle is between this range 10 to 25 degrees. So we can calculate the length of divergent portion using this empirical correlation. Right. So any questions so far?
सर फ्लो सेपरेशन एक बार रिपीट कर दें।
सर इसमें
Yes.
80 है
80 throat area. Throat area. This 80 जिसे हम AC से represent कर रहे हैं. That is throat area. So the length of this divergent portion is
फ्लो सेपरेशन एक दफा रिपीट कर दें सर।
okay. ये जो length of this divergent portion है, this length can be calculated using this formula. 15 into area of throat. What is 80? It is area of throat. This one. 80. Flow separation simply means, for example, here is the convergent part and here is the divergent part, which is very short. इसको compare करें इस nozzle से, इसमें convergent is short but divergent is long. So ये जो area है, this A2 and this A2 are same. दोनों में difference क्या है? Here you have divergent portion very long, ये जो portion compared to इस case में. Here this divergent portion is very short. So here when fluid will leave, it will not occupy this whole cross section smoothly. Fluid will be leaving like this one and some fluid will try to move in this direction. So that portion that is called flow separation. Now the fluid is not flowing in one particular direction or by occupying the whole cross section. यहाँ पे ये flow separation का phenomena नहीं होगा because the whole of the fluid will be occupying this whole cross section because divergence angle is not too large. Area of exit is same as here and here in both cases. यहाँ पे जो area at exit है, जो यहाँ पे area at exit of both are same, but here you will can have this flow separation. Right? Flow separation will drop the velocity. Here there will be no flow separation. Fluid will be flowing continuously or smoothly in the entire cross section or in the entire length of the divergent part. Okay. Okay. So that's why now we have seen that the convergent section is normally very small and divergent portion is very large. And we also now know that the maximum velocity occurs here in this portion. C is maximum in the divergent portion. And divergent portion is also of larger length, longer length compared to divergent section. That's why it can be assumed that all frictional losses occur after throat. Okay, so we can neglect the frictional losses effect in this portion because the frictional losses in this portion will be much larger compared to the convergent section. Because यहाँ पे velocity भी ज़्यादा है, convergent section, divergent section में velocity भी ज़्यादा है और इसमें length भी ज़्यादा है. So that's why the frictional losses after the throat are normally considered, and normally we can neglect the frictional losses in the convergent section. We can say that all the frictional losses are actually occurring only in the divergent section. So we have already stated why we need to keep this length large in case of divergent section. All right. So in other words, when we have neglected the frictional effect in the convergent section, and convergent section is actually responsible for the flow rate. We have already studied that this m dot through a nozzle is actually defined by the throttle, right? And if the frictional losses in this portion are negligible in the convergent section, it means whatever mass flow rate has developed here in the throttle section will be same after throttle, because throttle is actually describing or deciding the maximum mass which will flow through this nozzle, right? जो हम already पिछले lectures में study कर चुके हैं. So when we neglect the frictional losses in the convergent section, then it means coefficient of discharge is also 1. COD is also unity. Right? Coefficient of discharge is unity, means m dot divided by m dot s is equal to 1. M dot divided by, that is known as coefficient of discharge. Actual mass flow rate divided by isentropic mass flow rate. Isentropic mass flow rate is maximum, and that mass flow rate is decided by the throttle. Right? For flow from inlet to throttle, we have already said that if we neglect the friction here, so it means m dot will be maximum at the throttle, and after that, this m dot will not change. After throttle, m dot will remain constant. After throttle, so that's why this m dot will be maximum, which is m dot s. So m dot will be equal to m dot s because frictional effects here are negligible. So that's why coefficient of discharge is unity, because any friction after the throttle, जो भी friction है, it cannot affect the mass flow rate m dot, because m dot is defined by the throttle of the nozzle. Okay. Nozzles, ये जो nozzles अभी तक हम study कर रहे हैं, जी कोई question है किसी का? The nozzles which we have studied so far, these are actually, their axis is straight, right? That is, for example, if this is front view, so if you see from this side view, it will be like this one. Circular nozzle, then you will see a throat, and then maybe the exit area, the exit cross section. So such type of nozzle are actually these, their axis is exactly straight from inlet till exit. But in practice, you may have curved axis nozzles. We shall see in the next chapter where the turbine blades are shaped like nozzles, like this. So this is the nozzle which we have been studying so far, this one, with the straight axis. But here you can see nozzle shape cross section. Here you can see area is maximum, here area is minimum, and here area is again increasing. So it is, but here the axis is not straight, it is curved axis. Fluid is moving in this direction and then it is changing its direction. Right. So this is also a nozzle shaped area. So these are the nozzles which are used in steam turbines. So steam turbine blades, they are shaped like nozzles. So it means the axis of the nozzle can be straight like this one, or it can be curved. So these are also nozzle shaped area or nozzle shaped passages in which some fluid is flowing. Okay, maximum area, minimum area, making a throat, and again area is increasing towards the exit. So that is also acting like a nozzle. That is also a nozzle of curved axis. Right. So now let's solve a numerical problem. So in this problem, we shall not be assuming isentropic flow. So it means we have to account for the actual flow or the losses inside the nozzle. So here, let's see, gases expand in a propulsion nozzle. Propulsion nozzle, normally the nozzle which is attached to jet engines or rocket engines. From 3.5 bars and 425 degrees Celsius to a back pressure of 0.97 bar. Here I have already drawn the schematic. So here is the inlet pressure 3.5 bars and inlet temperature 425 degrees Celsius. Now the pressure at the exit is 0.97 bars. And the fluid flow rate through this nozzle is 18 kilograms per second. Taking a coefficient of discharge of 0.99. So we already know what is meant by coefficient of discharge. Actual mass flow rate m dot divided by m dot s is given as 0.99, and nozzle efficiency of 0.94. So it means nozzle efficiency is also given 0.94. Calculate the required throat and exit areas, means AC and A2 are unknown of this nozzle. For the gas which is flowing through that nozzle, the gamma is given, gamma is 1.333, and the specific heat Cp is 1.11 kilojoules per kilogram per Kelvin. Whatever the gas which is flowing through this nozzle, there its thermodynamic properties are also given. Assume that the inlet velocity is negligible. C1 is assumed 0. So gamma is given, Cp is given, and we first need to find out the area of throat. And to calculate area of throat, we know this equation that is given by m dot into V C at critical condition divided by C at critical condition. Now here it is written m dot s. So we can neglect the frictional effects in the convergent portion जो हमने डिस्कस किया. It means कि यहाँ जो nozzle efficiency given है 0.94, that is for the divergent portion only. For the convergent section, we can neglect any losses. So here we can see for the convergent portion, means from inlet till throat, efficiency is 1, and coefficient of discharge is also 1 if we neglect the frictional effects in the convergent portion. That's why यहाँ पे उसने m dot s लिखा है, m dot नहीं use किया. So here when we neglect the frictional effects in the convergent portion, then it will be m dot s, maximum possible flow rate, v dot c over cc. So now first we need to calculate vc and cc. And to calculate VC, we need to know PC and TC. Only then we can find out PV is equal to RT. Using that equation, PV is equal to RT, the specific volume, right? So PC over P1, we already know equation, just put the values and that is 0.54. So the pressure at rod PC is 1.89 bars. So इस क्वेश्चन में ये नहीं गिवन था कि whether it is convergent nozzle or convergent divergent nozzle, but you can now tell based on this value when PC is 1.89 bars. Here at rod pressure is 1.89 bars. Exit pressure is lower than 1.89 bar. It is 0.97. So it means it is a convergent divergent nozzle, right? Because this area at the throat is more than the area at exit. So it is a convergent divergent nozzle, and it is a choking nozzle because here pressure is higher and pressure will further drop in the divergent section till 0.97. Right. Okay, so PC is 1.89 bars. Now we can find out PC over T1 over 2 over gamma plus 1. So from here we can find out PC. T1 is also given 425 plus 273 Kelvin. Gamma is 1.33. So PC is 598.4 Kelvin. So now PC and TC, critical pressure and critical temperatures are known. So now we can find out CC, critical velocity 2 into H1 minus HC, which is 2 into CP into T1 minus TC. There is no need to use table or chart because it is gas, some ideal gas. Right? It is not steam. So we can use 2 into CP into T1 minus TC. So just values put together and find out critical velocity. So critical velocity for this gas is 470.3 meters per second. Now we can also find out the same CC using that equation, gamma RT critical. So we can use either this equation or this equation. दोनों से answer will be same. Gamma RT critical. So, but for using this equation, we need to find out R also, or we can find from here when gamma and Cp are known. So we also know this equation, Cp is equal to gamma R over gamma minus 1. So from here we can find out R, the gas constant. So now we can use this equation also to find out Cc. So either use this one or use this one because it is critical velocity. All right. So now we can find out critical, area at throat. So critical specific volume, R is known. जो हमने last slide पे देख लिया. Specific gas constant, P critical. So we can find out V critical. Right. So mass flow rate for oxygen, because here the mass flow rate which is given, that is for actual mass flow rate is 18 kilograms per second. But when we neglect the friction in the conversion part, so here mass flow rate will be the isentropic mass flow rate, which we can calculate using this coefficient of discharge is equal to m dot over m dot s. So m dot s is 18 kilogram per second divided by 0.99, which is coefficient of discharge. So m dot s is 18.18 kilograms per second. Because here in the convergent portion, the flow is still isentropic. Are you with me?
Yes, sir.
Yes,
All right.
sir.
So then area of throat can be calculated just by putting values. M dot S, VC, CC. So the units you should know. Take care of units. अगर कोई unit conversion है, you should know very well now. So the area of throat comes out to be 0.0339 meters square. Now, next we need to find out area at exit A2. So the same equation, A2 is equal to m dot 2 V2 over C2. Now C2 will be calculated using this equation, 2 into H1 minus H2. HC neo, right, will be H2. So 2 into Cp into T1 minus T2. So now we need to calculate T2. So how to calculate T2? That is the question. Now we cannot neglect friction losses in the divergent portion. because here nozzle efficiency is given. So it means we cannot use T2 over T1 वो जो equation हम use कर रहे थे. T2 over T1 is equal to T2 over P1 to the power gamma minus 1 over gamma. This equation was for isentropic process. And so far we were using this equation to find out T2. But this equation is for isentropic process. But the flow through this nozzle is not isentropic, right? Because efficiency is given. So then how to calculate this T2? So here we shall use the equation of nozzle efficiency. So for what was nozzle efficiency? Nozzle efficiency, the equation that was this one in terms of temperature. T1 minus T2 over T1 minus T2s. Here is the nozzle efficiency equation. 0.94, which is equal to T1 minus T2 over T1 minus T2. T2 is the actual temperature and T2s is the isentropic temperature. So first we shall find out T2s using this isentropic equation. So here we will say this T2 is actually T2s. So first we will calculate T2s and then we will put this T2s here to find out this unknown T2, the actual condition or actual temperature at the exit. Because 0.94, T1 is given, 0.94, the efficiency is given. So first we will use the same equation, this equation for isentropic process, but here T2 is T2s for isentropic process. P1 or P2, right? But temperature will be different if it is isentropic. So T2s is given as 506.6 Kelvin. So is T2s ko we will use here in the nozzle efficiency equation to find out T2. Okay, so by putting values, T1 is given, everything is in Kelvin. So to find out T2, 518.1. So you can see here, actual temperature is higher, 518 compared to isentropic temperature. Temperature क्यों rise कर गया? Because due to friction, some heat is generated. That heat is, some portion of this heat is transferred to the fluid itself. That's why when fluid is leaving this nozzle, its temperature is increased. So that's why the actual temperature is a little higher than the isentropic temperature, because there are 6% losses to overcome friction. लेकिन वो losses का भी जो major portion है वो गया कहाँ पे? वो उसी fluid को transfer हो गया in the form of heat. That's why its temperature is higher. ठीक है, इसको हमने ग्राफ पे भी शो किया, तो इसलिए दोबारा शो करते हैं. तो we are representing, for example, this process on ES diagram. Sorry, it is gas, perfect gas, so there is no need to show this dome. We are in the gaseous region. So in the gaseous region, these are the pressure lines. This is P1 and this is P2. So this is the ideal process, 1 to 2S. And this one is the actual process, T1 to T2. So here you can also see this T2 is greater than T2s. So that is shown here. T2 is greater than T2s. So now once P2 is known, we can put it here in this equation to find out C2. So just values put karte hain. Here you just remember to multiply this term with 10 to the power 3. Because Cp is in kilojoules, so we need to convert it in joules per kilogram. That's why 1000 se multiply 2 into Cp into T1 minus P2. So that will be C2, which comes out to be 632 meters per second. Right, so now C2 is known. Next, we need to calculate V2. So for V2, we know this equation for ideal gas. So V2 is equal to RT2 over P2. So just values put करते हैं, R हमने already find कर लिया था using this gamma and CP. So just by putting values here, you have to be careful. R is in joules per kilogram per Kelvin or pascals meter cube per kilogram per Kelvin. So that's P2 should also be in Pascal. So that's why 0.97 into 10 to the power 5. P2 is already calculated, 580. So from here, V2 is calculated, which is 1.48 meter cubes per kilogram. So V2 is known, C2 is known. What about M2? M2 will be the actual, because here the frictional losses are not neglected. So that's why the actual flow rate, which is given 18 kilograms per second, will be used. So A2 is equal to M dot 2 V2 over C2. Just values put 18, 1.48. So here is the area at exit 0.04 equal to meter square, which is larger than the plot area 0.0239. अब आप यहीं से अगर length of divergent portion calculate करना हो, so you can find out 15 into जो हमने equation देखी थी length of divergent portion can be calculated as 15 multiplied by area of plot AC, which is this one. So that will be the length of divergent portion, this length. This length should be kept as small as possible. इसमें कोई इशू नहीं है, it could be kept as small as possible. जो भी manufacturing के हिसाब से जो भी easily which we can produce smaller length nozzle वो हम कर सकते हैं, but here this length has to be calculated using this equation to keep this divergence angle in the range of 10 to I think 25 degree, 10 to 25 degree. So for example length ये divergence angle assume कर लें, then we can also find out this length L, right, to reach the same A2. A2 वही है जो हमने calculate किया, this one, this is the A2. यहाँ length find नहीं करनी, but if you have to calculate length, then that is the simple procedure to calculate length. जी, any question?
सर ये हमने
जी जी
T2S क्यों फाइंड किया था सर? ये
T2 क्यों फाइंड किया था?
T2S सर,
हाँ राइट,
आइसेंट्रोपिक टेम्परेचर।
जी T2 और किसी मेथड से कैलकुलेट हो नहीं सकता. T2 कैलकुलेट करने का हमारे पास मेथड सिर्फ यही है, नोजल एफिशिएंसी की इक्वेशन. Nozzle efficiency is equal to T1 minus T2 over T1 minus T2S. Here there are two unknowns, T2 and T2S. And what is T2S? T2S is this isentropic process के लिए. So for isentropic process we know this equation. जो मैं बार repeat कर रहा हूँ कि what is this equation? This equation is for ideal gas and for isentropic process. So isentropic process के लिए ये equation हमारे पास है. So first we calculate T2S from here. And then we use this T2S here in this equation of nozzle efficiency to calculate it. So even if it is non-isentropic process, still we need to use this equation to calculate T2S. उससे फिर हम T2 फाइंड कर रहे हैं. So अभी तक हमने जितने क्वेश्चन किए हैं उनसे जो डिफरेंस है वो सिर्फ यही है, यहाँ ये नोजल एफिशिएंसी की इक्वेशन यूज हो रही है to find out actual T2. ठीक है, मेजर डिफरेंस यही है, या कहीं कोएफिशिएंट ऑफ डिस्चार्ज आ गया 0.9. जी, एनी अदर क्वेश्चन?
सर ये जो क्वेश्चन में गैस एक्सपेंड लिखा हुआ है सर, हमें किस तरह पता लगेगा कि ये आइडियल है या नॉन आइडियल है?
Whenever there is a term gas, पहले भी मैंने एक्सप्लेन किया है, it is ideal gas. If it is not a gas, then there will be a term vapor or steam. ठीक है, तो जो न्यूमेरिकल्स या जो पोर्शन हम स्टडी कर रहे हैं इस कोर्स में, या इस thermodynamics के book में whenever the term gas is used, it is definitely an ideal gas. ठीक है, आप खुद अंदाजा लगाएं ना, अब ये कौन सी गैस यूज हो रही है propulsion nozzle में. Of course it will be air which is burnt inside this nozzle. एयर नॉर्मल टेम्परेचर और प्रेशर के ऊपर भी आइडियल है, तो इतने हाई टेम्परेचर के ऊपर 425 के ऊपर तो डेफिनेटली आइडियल गैस ही होगी, ठीक है, बिकॉज यू आर मूविंग अवे फ्रॉम द डोम ऑफ एयर. सो ऑलरेडी टेम्परेचर और प्रेशर इतने हाई हैं कि इट इज डेफिनेटली एन आइडियल गैस. ठीक, तो अगर यहाँ स्टीम होता तो डेफिनेटली इट इज नॉन आइडियल. तो यही दो क्वेश्चंस आप इस पूरे चैप्टर में देखेंगे, आइदर गैस और स्टीम. गैस में समटाइम्स वो स्पेसिफाई कर देगा कि एयर है, हीलियम है या ऑक्सीजन है. समटाइम्स स्पेसिफाई नहीं करेगा, जस्ट ये बता दिया उसकी प्रॉपर्टीज. सो इफ यू लुक, बिकॉज प्रोपल्शन नोजल में इट्स नॉट प्योर एयर, एयर है प्लस उसमें जो फ्यूल बर्न होता है तो उसकी जो प्रॉपर्टीज है वो प्योर एयर वाली नहीं रहती. सो वो जो उसकी प्रॉपर्टीज है वो यहाँ शो की, बिकॉज फॉर प्योर एयर इट इज 1.4 gamma, but here it is mixture of air which is flowing, so उसके लिए जो approximate gamma और approximate Cp है वो यहाँ शो किया. जी, any other question from this example? Okay, if there is no question, so then let's move forward. The next topic is steam nozzles. अभी तक जो हम नोजल पढ़े थे वो इन जनरल पढ़ रहे थे. It could be an air nozzle or gas nozzle, or it could be a steam nozzle. But now we shall specifically study about steam nozzles. So now one thing is clear that here when specifically it is written that it is steam, so it means a non-ideal gas. So for steam nozzles, now we shall solve certain problems related to steam nozzles and some specific phenomena which are only relevant to steam nozzles, which do not occur in gas nozzles or air nozzles. So वो सब हम इस topic में study करेंगे. So for steam nozzles or for steam calculations, we know the properties, thermodynamic properties of steams can be obtained from tables or from the HS chart if it is available. So to find out these critical pressure ratio or critical velocity or maximum mass flow rate, the formulas which we have already derived for ideal gas can also be used for steam, like this one. PC over P1 is equal to 2 over gamma plus 1. Here we are using an approximate value of gamma. For dry saturated, it is 1.135. So here is the critical pressure ratio if the steam which is flowing into the nozzle is dry saturated. So that is the critical pressure ratio for dry saturated steam. Similarly, for superheated steam, this gamma or N or K is assumed as 1.3. So the critical pressure ratio for superheated steam is 0.546. Right. Temperature at the throat, that is the critical temperature, can also be calculated using the same equation, Tc over T1, or we can use this method using steam tables. This is convergent nozzle. Right, and here we want to calculate Tc, so we can use 2 over gamma plus 1, or if we know Pc from this equation or from this equation, then we also know S1 is equal to Sc. Right. So now we know these two properties, pressure and entropy, and using these two we can also calculate T critical from the steam table or HS chart. Okay. And then critical velocity can also be calculated using H1 minus Hc. Here H1 and here Hc. HC, again, you can calculate using PC and SC from tables or charts. So we can calculate HC and PC using charts or tables for a known critical pressure and entropy. Or वैसे भी in the conversion part, we can assume isentropic process. Right? So that's why SC is equal to S1 can be assumed. All right. So now we shall now derive another equation of calculating the change or drop in enthalpy, delta H. So far, we have learned how to calculate this enthalpy drop, means from inlet to exit H2, H1 or H2. In case of steam, we use steam table or steam chart to calculate this enthalpy. But now there is one more equation also to calculate this enthalpy drop for a fluid flowing through the nozzle. So let's derive an equation also. कि अगर table भी नहीं है, chart भी नहीं है, या कोई equation भी नहीं है, then कोई simple CP delta T भी आप use नहीं कर सकते. Then there is one more equation to calculate this enthalpy drop. So now we shall derive that equation also. So let me erase it. आपकी क्लास की टाइमिंग कब तक है? 11 o'clock.
Yes, sir.
Yes, sir.
Yes, sir.
So for isentropic flow, that is equation dH is equal to VdP, or Vp to the power 1 over K is equal to constant. This is something we already know from this equation. Here PV is equal to
सर एक क्वेश्चन है
जी जी
सर, जो आपने पहले जो हमारी फिजिकल क्लासेस थी उसके अंदर आपने क्लासेस ली थी तो इक्वेशन लिखी थी जिस तरह ये सेम लिखी है T2 over T1 इज इक्वल टू P2 P1 होल पावर gamma minus 1 over gamma. लेकिन सर अभी जो लास्ट आपने न्यूमेरिकल किया है उसके अंदर ना ये शफल थी, मतलब कि T1 over T2 इज इक्वल टू P1 over P2 होल पावर gamma minus 1 over gamma. तो उस टाइम मैं समझा शायद मेरे लिखने में गलती हो, लेकिन अभी दोबारा वो इक्वेशन आई है.
अच्छा, ये सिंपल कैलकुलस है. आप यहाँ पे डिनोमिनेटर और न्यूमरेटर को चेंज करते हैं और यहाँ पे भी चेंज करते हैं. पावर्स में
लेकिन सर पावर्स में कोई फर्क नहीं आएगा.
बस सिंपल मैथमेटिक्स.
ठीक है, चलें, सही है.
ठीक है. अगर आप कहें कि दिस इज T2 over T1, बट इससे आप इसे आप T1 over T2 कहें और इसे P1 over P2 ना करें, then it is wrong mathematically. So mathematically आप इसे T2 by T1 लिख सकते हैं और इसको अगर इसे T1 by T2 करें, so you can write it here also P1 by P2.
ओके सर, ठीक है, थैंक यू.
Okay. Now we know this equation. So this equation also telling us that this equation को अगर आप देखें, so that is actually telling us PV to the power K is equal to a constant. Is it correct? Mathematically. ठीक है, ऐसे चेक कीजिएगा. आपने जो बेसिक कैलकुलस पढ़ी हुई है, PV we can say this thing, PV to the power K, or P1 V1 to the power K, or gamma is equal to P2 V2 to the power gamma over K. ठीक. This thing can be written like this one, right? Or I can say it is Vp to the power 1 over K is equal to V1 P1 to the power 1 over K is equal to V2 P2 to the power 1 over K. ठीक. So this is correct. यही इसका वर्जन है, सेकंड वर्जन, यही इसका एक थर्ड वर्जन. all these are actually correct. Okay. From simple mathematical or calculus which we have learned. Okay. उसी की बेस के ऊपर, इसी इक्वेशन की बेस के ऊपर, is written here for, and this equation is for isentropic. S is equal to constant from 1 to 2 per case में. So that is written here, Vp to the power 1 over k for an isentropic flow. Now what is this thing? VdP is equal to dH. Now let's see what is this. VdP is equal to dH. ये अगर क्लियर नहीं है तो let's discuss later on. अगर आप इसमें कोई शक है, because it is the basic mathematics. Now I will explain this second term, dH is equal to VdP. ये कहाँ से आया? So between any two states, 1 and 2, I'm writing that dH from this equation, dH from 1 to 2 is equal to VdP from 1 to 2, by integrating the change from 1 to 2. Now what is this equation? Here is what we have learned in Thermo 1 for second law of thermodynamics, or for reversible flow, we already know dq is equal to T into ds from entropy equation. Clear? dq is equal to TdS. And also from first law of thermodynamics, dq is equal to du plus pdv, or du plus w, del w, which is actually pdv. This equation is also clear, right? From first law of thermodynamics, del q or del u is equal to del q minus del w, or minus del w का opposite side पे लेंगे, so that's why it is pdv, right? So here we can replace this TdS. Del dq can be replaced with TdS. So now this equation is TdS is equal to du plus pdv, right? और इसी को आप लिख सकते हैं in terms of enthalpy, du is equal to dH minus d into pv, या नहीं? It is clear, because enthalpy is equal to u plus pv, or u is equal to h minus pv. But here it is du, so du is written as dH minus d into pv, plus ये pdv as it is आके. ठीक. अब आप इसको डेरिवेट कर लें. It will be pdv plus vdp. See होगा with, so pdv will cancel with this pdv, and what is left? V into dp here, right? So TdS, the same TdS is written in terms of enthalpy minus vdp. And for isentropic process, change in entropy is 0, so that del ds will be 0. So this portion is 0. So now we can write dH is equal to VdP. dH is equal to VdP, which is shown here. dH is equal to VdP. That comes from here. This one, the previous knowledge. Right. So here for now, इसी equation को now we are integrating from state 1 to state 2. 1 to 2 dH is equal to 1 to 2 VdP. Right. And now इसको further हम expand करेंगे. So H1 minus H2 is equal to, actually it is H2 minus H1. So we say H1 minus H2 लिखेंगे, so then this minus will be shifted here, minus 1 to 2 VdP. Now next step. Now what is done here is equation को उसने इस form में लिख दिया. Does it make any sense or not? यहाँ पे देखिए उसने किया क्या, इस equation में उसने दो terms introduce की. उसने यहाँ पे इंट्रोड्यूस किया P1, इस इक्वेशन में P1 to the power 1 over n into P to the power minus 1 over n. इसको मैं भी so this is VdP into P to the power 1 over n into P to the power minus 1 over n. Does it make any change? ये VdP ही रहेगा ना, that will be, जब ये powers add हो जाए P to the power 0, कोई चीज कुछ चेंज नहीं हुआ इस इक्वेशन में. Now let's introduce one more thing. V to the power n into 1 over n. इसी V को you can write it like this one. V to the power n into 1 over n. So still, so इस V को मैंने यहाँ से delete कर दिया. Now it is written like this one. So it is still VdP. This whole term is still VdP. This is V, this is dP. That is nothing. This one is P to the power 0 actually. 1 over n minus 1 over n. Clear? This equation is written like this.
Yes, sir.
अब क्या किया इसमें, इसने ये Vp to the power 1 over n और 1 over V और PV to the power n, ये Vp to the power 1 over k is also equal to, ये मैंने अभी बताया था, isentropic process PV to the power n और k और gamma is equal to a constant. So अब यहाँ पे उसने क्या किया है, इस P और V को सेपरेट कर लिया. That P and V are separated here. PV to the power n is equal to constant. PV to the power n और whole power 1 over n. ये 1 over n इससे भी multiply हो रहा है, 1 over n इससे भी multiply हो रहा है. ठीक. Because now this is a constant, so we can write it as P1 V1 or P2 V2 to the power n or P3 V3 to the power n. That is a constant. ठीक. So from here till here, it is also okay mathematically. P to the power minus 1 over n into dp ये सेपरेट कर लिया. ठीक है, इन दोनों को सेपरेट कर लिए. 1 over n is whole power 1 over n और inside p into v to the power n. Now pv to the power n for an isentropic flow, that is from this equation. pv p1 v1 is equal to p1 v1 to the power k is equal to p2 v2 to the power k and so on. That is from here for an isentropic flow. Right, so dH is equal to minus VdP, and this term is now written in this form. Okay. Mathematically, if there is any doubt, then ask. Otherwise, mathematically, it is correct. Now I can write it as P1 V1 to the power n or P2 V2 to the power n. This equation, because that is a constant for an isentropic process. Right, so far. Because this PV to the power n is equal to a constant. Okay. So this is a constant. इसे आपने separate लिख दिया और इसे integrate कर दें. That is a variable here. P to the power minus 1 over n into dp. That is a constant. Right. So that is written separately. और इसको आपने integrate कर दिया. P minus 1 over n plus 1 over minus 1 over n minus 1. Right. और लिमिट्स अप्लाई कर दी 1 to 2. Right. Any question from this step till this step? Means it's clear. So now you can further simplify this thing. So this term will be written outside. यहाँ पे लिख दिया इसको. This term is written here, minus n over n minus 1 into p2 to the power 1 over n into v2. ये 1 over n उसने inside multiply कर दिया because this is a constant. Inside क्या, what is remaining? p2 to the power n minus 1 over n minus p1 to the power n minus 1 over n. Right, G? That is also clear from this step till this step mathematically. ये derivation book में नहीं है, किसी और source से ली हुई है. Right. Next, so further simplify कर लें. Now we can multiply this inside When you multiply this term with P2, then it is P2 V2 into P2. When you multiply this term with this P1, then it is P1 V1. P1 to the power 1 over n V1 into P1. Right. So जब इन दोनों को multiply करेंगे, it becomes P2 V2 minus इसी को अब इससे multiply करें. So that is P1 into P1 to the power. ये दोनों powers add हो जाएंगी. V1. So it comes out to be P2 V2 minus P1 V1. इन दोनों powers को add कर दें, it becomes 1. Right? So P2 V2 minus P1 V1. और इस माइनस को अंदर शिफ्ट करते हैं, so then it is P1 V1 minus P2 V2. So that is the equation which is given in the book in terms of K over K minus 1 into P1 V1 minus P2 V2. What is this equation? That is actually pH, what we have derived to calculate the enthalpy change from state 1 to state 2 for an isentropic flow. Here we have this equation. For an isentropic flow from 1 to 2, the change in enthalpy can be given by this equation. बुक में इस बुक में उसने k यूज किया है, ये जहां से मैंने डेरिवेशन ली है वहां वो k की बजाय n यूज कर रहा है, so that's why you see here n. Right. So now we have one equation also of calculating the change in enthalpy, because in nozzle calculation we are interested to calculate the change in enthalpy from state 1 to state 2. And for that change in enthalpy, agar steam tables nahi hai, charts nahi hai, then we have this equation also to calculate the change in enthalpy. Right. Any question from this slide?
No, sir.
Okay जी, so इसी equation
सही जो k कांस्टेंट है इसकी क्या वैल्यू होगी?
k है क्या? Cp over Cv.
ओके
जिसे गैमा कहते हैं.
ठीक है सर. ओके
मैं आपके दोबारा से लिख दूं गैमा और k और किसी बुक में n, all means the same thing.
ओके सर, थैंक यू.
Isentropic index भी कहते हैं जो k है ना, isentropic index और specific heat ratio, it is the same thing. ठीक. k n, तो ये मैंने जहाँ से डेरिवेशन ली है वहाँ पे उसने n यूज हो रहा था. बुक में, इस बुक में मैकॉनकी की बुक में वो a यूज कर रहे हैं, कहीं पे गैमा यूज हो रहा है. ठीक है. और नॉर्मली फॉर आइडियल गैस वी यूज गैमा, फॉर नॉन आइडियल गैस वी यूज k और n. ठीक है. So it means the same thing. So now we have this equation also of calculating enthalpy change for an isentropic flow. Delta H is given by this equation, or this enthalpy change is also equal to change in kinetic energy for nozzle. So it means this change in kinetic energy is equal to this equation. Okay. So अब इसी equation को हम आगे further use करेंगे to calculate the to find out an equation of maximum mass flow rate through a nozzle. What is the maximum possible mass flow through a nozzle, or maximum possible velocity which we can get through a nozzle? We shall now derive equations for this one using this equation. This equation से आगे हम आगे further दो equations derive करेंगे. Okay, so which we will do in the next class, जो आपकी 2 o'clock के बाद. ठीक है जी. So I stop here. So we should meet again.
सर ये जो सब इक्वेशन जो हमने टाइप किया है सर, ये आइडियल गैसेस के लिए है सर?
ये जो इक्वेशन है, हाँ जी, इसमें हम एज्यूम आइसेंट्रोपिक कर रहे हैं और आइडियल कर रहे हैं. राइट, बिल्कुल उसी के लिए.
थैंक यू सर.
बिल्कुल आइडियल गैस के लिए. स्टीम के केस में इन गैसियस रीजन, जब स्टीम इन गैसियस रीजन है, मिक्सचर रीजन में नहीं है, तब भी हम इसको यूज कर सकते हैं विद के की जो एप्रोप्रिएट वैल्यूज है. ओके जी. सो 41 are present. Okay. और यहाँ पे अटेंडेंस कितना ने लगा दिया? अटेंडेंस में 67 प्रेजेंट है। ये गूगल क्लासरूम कोड ही नहीं पता है, उमर हयात खटक, इसके साथ प्लीज
Yes,
ये गूगल
sir.
क्लासरूम शेयर कर लीजिए।
सर ये 18 बैच का
ये डी सेक्शन, ओके चलो ठीक है, मैं उसके साथ
बैच